Okay, welcome everyone to another TSVP talk. This week we are very pleased to be joined by Ken Ono from the University of Virginia. Hopefully many of you were able to see Ken's lovely talk on Tuesday in his presidential lecture. He also gave a more technical talk in my own unit seminar. So Ken is, as the screen indicates, he has many accolades, including being STEM advisor to the Provost at UVA and being the Marvin Rosenblum Professor of Mathematics. One thing I didn't mention on Tuesday is that kind of part of how this visit was initiated is because Ken and I know each other because we overlapped for a single semester, I think, before I joined OIST and after Ken joined UVA around that time. So it's great to be able to welcome him to Okinawa. I hope he's had a great time. I hope everyone's enjoyed seeing his talk so far and will enjoy this one as well. So please give a warm welcome to Ken, who's going to tell us all about swimming in data.
So thank you for coming. I have had a great time, ate way too much, got a lot of sun, and hope to come back. I'm going to give this talk with I'm a little bit nervous about this talk. So this talk that I'm going to share with you is very lowbrow. And in fact, this is a talk that I'll be giving at the end of August at the Olympic Training Center in the U.S. Olympic Training Center in Colorado Springs, where the intended audience are coaches and members of the various national governing bodies as part of the U.S. Olympic movement. In other words, there will be no scientists in that room. And the charge that I was given was, how do you do what you do as a scientist and actually help athletes? Because there are lots of people who write papers in sports science, writing papers that are kind of irrelevant to coaches. And so in attending this lecture, please understand that I assembled these slides for that audience. I think it'll be very fun. I'll show you some swimming races. I think the results will speak for themselves. And if you want to dig in a little bit deeper, that will have to be another time. Okay, is that okay? Great. The World Swimming Championships are going on right now as we speak in Singapore. Some of the athletes I'm going to talk about have already won World Championships. And yeah, I think the work, like I said, I think it kind of speaks for itself. So just to begin with, and to keep in mind that this is, again, a talk that I'm going to give to coaches, I will begin that talk as I will begin this talk, sort of saying a little bit about my personal background. So I'm a scientist. I was originally trained as a mathematician. If you're interested in objects called modular forms, they arise quite naturally in number theory. And part of my work has overflowed into bits of theoretical physics, mostly in the stringy corner of algebraic geometry and number theory. And in particular, I've been able to collaborate some with Hiroshi Oguri and his group. And I think many of you met with Hiroshi yesterday. He's part of your visiting team. He's really a fantastic scientist. And this is an image that I stole from the internet. And a long time ago, I still love sports. I love sports. And a long time ago, I was kind of a participant in sports. Early in life, when I was in high school, most of the decade of the 1980s, my dream was to be a bike racer. And this is proof that you can lose hair in life. Or maybe I should say this is proof that I once had a lot of hair. But in the 80s, maybe I had too much hair and I'm paying the price for it now. As a graduate student at UCLA, I didn't have as much time that cycling requires. So I picked up running. I wasn't very good at it. But yeah, I did some road running in the 1990s. And much later in life, after I moved to Atlanta, where I was a professor at Emory University for 10 years, I picked up triathlon. And I was in particular really interested in the off-road triathlon, where the cycling is actually on mountain bike trails. Really nice. So I've thought about cycling for most of my life. I've been familiar with running for most of my life. And when I became an age group triathlete, I had to learn how to swim. And it was very humbling, very humbling. It's a good thing that I was horrible at swimming, because when you're horrible at swimming, you quickly learn what some horrible tendencies are. And as I will begin to describe in this talk, I had to translate that personal knowledge of being a poor swimmer into how do I translate what I've learned with my hands? How do I translate what I'm going to learn through some engineering and some mathematics to make talented swimmers even faster? So how did this happen? It happened completely accidentally. I had an undergraduate student at Emory. His name was Andrew Wilson, who was a brilliant math student. He actually he was admitted to MIT, Oxford, and University of Texas for graduate work in mathematics. So that tells you something about his academic pedigree. And so I was delighted to have him as one of my personal thesis students in number theory. He ended up working on elliptic curves, and he was quite interested in the problem of detecting primes from non-primes using various properties of these curves. But if you were to have met him 15 years ago or 12 years ago and asked him what he was really passionate about, it wouldn't have been mathematics. He wanted to be a great swimmer. And in high school, he played water polo. This is soccer, but in a pool where it's really kind of a crazy sport. So he knew how to swim, but he didn't know how to swim like a competitive swimmer would consider swimming. At Emory, Emory is not well known for its athletic program. In the United States, collegiate sports is divided into 3 divisions. There's Division I, which is essentially professional, pre-Olympic. There's Division II, which is not. And then there's Division III, which is everybody else. So Division III, if you are familiar with collegiate sports in the United States, that is the division where it is still possible for you to be a student athlete, both pursuing your sport, but actually taking your academics quite seriously. If your image of athletics at the highest level doesn't mix well with pursuing an advanced degree, that's basically, that would basically be correct. So anyway, Andrew showed up at Emory as a converted water polo player, and he was a very slow swimmer, very good math student. How slow was he? He was the slowest swimmer in the pool. The girls on the team were all faster than him. And it was remarkable that the coach allowed him to practice with the team. Yeah, and Andrew's dream was to get good enough to be invited to travel to one meet on this Division III team. Well, so Andrew and I started to think about swimming shortly after Yves Meyer won the Abel Prize in Oslo. So I was part of the delegation that celebrated the Abel Prize that Yves Meyer won. Yves Meyer is very well known for giving birth to a large part of mathematics involving the theory of wavelets. Ingrid Dobeschies is someone else who you might know that is in that group. And well, at this conference where they give out the Abel Prize, the Norwegian government invites many of their best scientists to mingle with the mathematicians from abroad. And everything I'm about to tell you started over a little table with shrimp and cream cheese and cocktail sauce, trying to make small talk with Norwegian mathematicians. And I think I said something really rather insulting along the lines of, why is it that the Norwegian cross-country skiers are the best in the world? They beat everyone. And I'm pretty sure I said something that I shouldn't have said. Is it because you don't have sun, I mean, or it's always cold, or I said something pretty insulting. And how lucky, because the professor said, no, I am a professor of cross-country skiing. I head the unit at the Norwegian School for Sports Analytics, and we study it. And that's the beginning of this story. And I wanted to understand what they had done. And that was, in my opinion, the first example where scientists worked very closely with athletes, where the goal isn't to write 10 papers in a sports journal that nobody in the sport would read, but they wanted the results to speak for themselves. And that was important to me. So we tried to emulate some of the things that they did. It was very difficult, but so how did it turn out? So Andrew was a walk-on in the 2014 team. That means you begged to have a spot in the pool for practice. We studied the science of swimming, and it took off, and he won an Olympic gold medal in Tokyo in 2020. He went from the worst swimmer on a Division III team, including all of the girls, to Olympic gold medal. And now I want to tell you how that happened. Is that interesting? This is a true story. And here's Andrew, right, when he finished his thesis. And this is what an Olympic gold medal looks like. So we've been doing a lot of this. So in Tokyo, the athletes that I've worked with won a bunch of medals. Here's Andrew down here. Some of these names, if you follow the sport of swimming, you might know. They include world champions and some of the main figures in sports today. Erica and I were very lucky. We got to go to Paris last year for the Olympic Games, and we did even better. And so we won a bunch of medals. Some of these names, I'll tell you, Kate Douglas is one of the best swimmers in the world today. Thomas Howman, we started working with him when he was 14. He won Olympic silver medal as a high school student. Taylor Knibb is perhaps one of the best triathletes in the world. Because of my background in cycling, I love talking to her about cycling. And on our lark, her coach told her that for practice, she should do a few bike races because cycling is one of the legs in triathlon. After you swim, you bike ride. And Taylor last year in her second bike race ever in life won the US National Championships. So she actually competed in the Olympic Games in cycling and triathlon. And I think the Olympic time trial bike race was like her third or fourth bike race ever. It's crazy. And yeah, these are some of the athletes that we've worked with. Together with the Olympic head coach, Todd DeSorbo, who is the head coach also of my University of Virginia team, we work very closely together. We started a company called Velocity Swim Labs, and athletes from all over can come work with us using and taking advantage of some of the things that I will be showing you. Where do we stand today? Actually, I have to update this. Oh, I don't have to update because the plus is there. But presently we have 12 world records. Our athletes have broken over 50 American records. And this is true. If you count Olympic and world championship medals, we've won over 100 in the last 5 years. Already at the world championships this week, Gretchen Walsh is a world champion in butterfly. She just missed breaking her own record by, I think, 0.2. Alex and Kate have already won medals. And so, yeah, we probably already have 7 or 8 medals from this world championship. So, yeah, let me tell you how this works. This is interesting. Okay, yeah. So here's Kate Douglas. She's actually one of my graduate students. She's earning her graduate degree in statistics. We've even written papers in science, but that's not for today. At the Olympics last year, she won the gold medal in the 200-meter breaststroke. She's a favorite to win the 200-meter tomorrow night in Singapore. She won an Olympic silver medal in the 200 IM, and in Tokyo, she was a bronze medalist. She keeps getting better. This is what it looks like to win an Olympic gold medal. This was the night she won her gold medal in breaststroke, and it's so exciting. It is so exciting. The family is there. 4 years of hard work, working through the days when you were sick, juggling your schoolwork. So yeah, that was a super happy moment. And yeah, I'm glad I got to be part of that. So I think it's important to do a little bit of telling, but I want to show, right? I want to show you some races. And so this is a race from last December. It's a World Cup event in Asia. And many of these names are among the top 20 breaststrokers in the world. And let's just watch the race. Yeah.
Douglas and Shmush going 4 and 5, a world record.
Yeah. Oh, hold on.
Valuable.
Yeah. So 1 through 8 is not first, second, third, fourth through eighth place. These are the lane assignments. So the fastest swimmer is given a middle lane assignment, usually 4 or 5. So here's Kate Douglas. So watch lane 4 and just listen to the commentator.
Douglas and Shmushka in 4 and 5. A world record would be so valuable for Douglas here, not just with the bonus money, but of course the point score.
That's Kate.
Against her teammate and great friend Regan Smith. 14.1, she swam last week.
Make it a little bit louder.
Big crowd here on hand to watch Kate Douglas, the world record holder in this event, the women's 200 meters breaststroke. There she is, top of the yellow lane. She's already got the best of the starts and the pullouts. And as she swims through only 4 strokes on the first lap, the best part of her stroke in this event is just how efficient she is and how streamlined she is in each stroke. There she is in the black cap, Kinder above her in the green cap, and Shmushka there in lane 5, trying to push the pace and match that of Douglas through the first 50. So Douglas, under world record pace through the first 50 meters, 30.4 in fact. How about that as an opening split of the 200? She's streaking away already at this point, and similar to what she did in Paris to win the Olympics, Douglas is going to push through the first 100 or even 150, try and build up a lead, of course, that lead over a world record line, and see if she can hang on and swim her personal best. So Douglas, how about that? 3 body lengths ahead, 0.6 under world record at the 100 meters split, 104.0. It's less than 2 seconds off the 100 meter world record, actually. So Douglas, she rested last week, that final day of competition in Incheon. She didn't swim the 200 IM, and that extra day of rest might just be giving her that little bit more energy tonight here in Singapore. So starting to increase her rate now is Kate Douglas, bringing those hands up and over the water, trying to be a little bit more aggressive in terms of the style we normally see from her. She's a whopping 0.87 under world record with just 50 meters to go. I can't see her missing this one. She's swimming so confidently in 2024 is Kate Douglas, building her rates. She might even be getting faster and faster. This is monumental here for Kate Douglas. A full second under world record pace. That line's at her feet, and she's swimming away from it here in Singapore. Douglas in front. Don't worry about the crown. We're looking at the world record. Douglas comes in, and it is a new world record. 212.72. Kate Douglas, she can do it all. Gold in Singapore. It's a triple.
So 2 weeks later, she took another 2 seconds off her world record. The commentator wasn't right. She was not rested for that event. Yeah, so let me tell you about Kate Douglas. This is a picture of Kate Douglas coming out of high school in 2016. And she was recruited to my university, University of Virginia, as a sprinter, very short distances, 50 meters, 100 meters. As a 15, 16-year-old, she still holds the 50 freestyle record for high school students. But she did not come to the University of Virginia to be a breaststroker. And when I started working with the team, I conduct a bunch of tests that doesn't look like swimming on each of the athletes to figure out what strengths each of these athletes have with respect to different movements. And I try to assemble the swim theoretically from the movements and the measurements that we collect. And shortly after I had my first session with Kate, I remember telling her parents and the coach, saying, I know you recruited Kate to the University of Virginia to swim these sprint events because there's so many of them and that's valuable for team competition. But she really has the tools perhaps to be the best breaststroker in the world. And I think people thought it was crazy because at the time she had not yet trained for breaststroke. And already at the University of Virginia, 6 or 7 of the women were better than she was. She wasn't even on the depth chart. But here we are now. She's world champion. She's world record holder. So how did that happen? This is Kate now. After her first year in college, she never lost a race in college ever again. She holds 15 individual and relay records. And yeah, this was us a couple years ago when we were just getting started. Now we have many more of these. Yeah. So what is it that we do? Okay. What is it that we do in terms of testing these athletes that we communicate to the coaches that allows them to develop precision training? You go to a swimming club and you watch a coach marching back and forth along the pool with a stopwatch, it'll look like everyone in each one of their lanes is doing exactly the same thing. Okay, that's not how you make a world-class swimmer. You make a world-class swimmer or world-class anything by precision training. So how do you determine what precision training will be for each of your athletes? Well, I apologize for this audience that I'm going to go through this, but yeah, what is swimming? Swimming is the application of forces to move the body, move and control the body through water. And humans are not, we're land creatures. Our biology is not well designed for swimming. When you go out for a run, a long run, maybe 3 kilometers or 5 kilometers, when you get home, your quadriceps are in pain, they hurt. And why do they hurt? Because you are trying to counteract the forces of gravity as your primary opponent when you are running. And that's not actually at all apparent in swimming. It's a completely different ballgame. So in swimming, unlike running or most land-based sports, buoyancy, your buoyancy in the water is actually minimizing the effect of gravitation. And so your main obstacle, and I think you all know this, but we need to make this a little bit more scientific. Our main obstacle is drag. How do you minimize drag? How do you compute the drag coefficient for each athlete in each position in each of the 4 strokes that they might be swimming? I think we're the only group in the world that actually collects that sort of data, but we don't want to guess. Yeah, so what is swimming? Well, a sailfish totally knows how to swim. Without any effort, this fish can go 80 miles an hour with just the bare minimum of effort compared to what Michael Phelps has to do to swim 20 seconds, 6 miles an hour. Okay, huge difference. So what are our main obstacles? Well, we have to think about Newton's laws of motion, of course, and just a very quick recapitulation for this audience. Newton's first law of motion is indicated by this cartoon. A body in motion remains in motion, or a body at rest remains at rest. Needs some force applied to it. The second law of motion is the famous equation, F equals ma, force equals mass times acceleration. There's very little you can do about changing an athlete's mass, but there's a lot that you can do in terms of studying its acceleration as well as deceleration. And the third law of motion, for every action, there is an equal and opposite reaction. If a swimmer is moving water behind them by taking a stroke, they dart forward, and we want to capture data in a number of different ways with the goal of assembling drills and research training programs that will assist each athlete. So here's the simplest equation for swimming. This is the drag equation in fluid dynamics. So you have to deal with viscosity, but again, the only things that you can work on now for an athlete will be the drag coefficient and improving fitness and streamline to make the acceleration much more effective. So if we don't want to talk about equations, this picture sort of says everything. Swimmer A on top and swimmer B on top might be equally gifted in terms of their physical capabilities, but I'm sure you can see the swimmer on the bottom is going to be much slower. By dragging their legs, the drag coefficient goes up. And this is, of course, a very simple example of something not to do when you're swimming. By the way, it's very hard to not do this. Minute changes in execution often result in the dropping of the legs. If you don't rotate your head properly when you take a breath, the legs go down. If you look up when you're not supposed to look up, the head goes down. So we have studied very carefully all of these various kinds of correlations, and in particular, for each individual athlete. So how do we do this? Loosely speaking, we have a number of tools and devices at our disposal. We use accelerometers. We use force paddles and high definition video to assemble an athlete's digital twin. Maybe many of you actually are into digital twinning. This is not new, but the digital twin allows us to optimize and assemble a formula, a recipe for each athlete that's optimal in their event. And the goal is, through the course of the training block, to get to the point where in championship season, the athlete is able to race their own digital twin. Okay, and that is very, very hard to do because there's lots of factors that come into play. Do you have the cardiovascular ability to take as few breaths as we might ask? Do you have the ability to perform certain kinds of body movements? And often our recommendations have the property that the answer is no, but you have 6 months to get there. Great. So just to give you an example of some of the things that we look at, if you're a swimmer, I think many of these things will mean something to you, but there's a very long list. There's several dozen things that we try to optimize in each of the strokes. So of course we want efficient turns. If you ever go to a gym, maybe do CrossFit, you know what a box jump is. It measures the explosiveness of your jump, which should translate into explosive pushes off the wall. Much more easily said than done, because you have to do it in water. You want to optimize the number of dolphin kicks. Very, very difficult to execute. Optimizing timing. You have to worry about cavitation, right? So all of the things that you might think would be important to swimming fast, we study. Let me say one sentence very clearly. The Olympic champion, the world champion in swimming, is rarely the best swimmer. Let me say it again. The Olympic champion and the world champion is rarely the best swimmer, because the best swimmer probably doesn't have to worry about walls or the other rules that correspond to the event. The best swimmers in terms of championships is the swimmer who slows down the least. And so that is our perspective. I can get up to 6 miles an hour swimming for maybe 5 meters, right? Michael Phelps can do that for a whole 200 meters. I can do that for 5 meters. If I just didn't slow down, I could be Michael Phelps. Because obviously I'm exaggerating, but I cannot tell you how many races are won. 90% of the races that we win, and we're high-fiving at the end, is because we knew here are the 10 spots where an athlete is going to lose. Make sure that those didn't happen. And there's so much parity in the pool that is really the secret. Great. All right. And what we do is we offer advice for precision formulas for each of the athletes with the goal of being able to execute those formulas in championship season. I said very carefully earlier that Kate Douglas never lost a race after her first year in college. And there's a story behind that. After her first year in college, she only won, it sounds funny to say it this way, she only won 1 national championship. She got a bunch of seconds and thirds in her other events. And we analyzed that. And we came up with a list of targets of opportunity that, if she corrected, would translate into almost near certain victory. And in her case, the most prominent one was her cardiovascular effort. She's a fish in the water, but she wasn't very strong cardiovascularly. So we wanted to get to a point where she could execute these kicks called dolphin kicks that are very powerful underwater, but execute them off each wall through the course of a long race. And these kicks rob you of oxygen. And she wasn't able to do that. So her main goal in college was to build the her vascular system. And well, she never lost again in college. Now I want to go back to the breaststroke. Because, as I said, she's world champion, but when she arrived at the University of Virginia, she was not even on the depth chart. The coach would never have thought to put her in a breaststroke event. So what did we do? I'm going to show you some data that we collected on her swimming. This is not Kate. This is another swimmer. His name is Sebastian Sergile. In the pocket of that belt, there is a waterproof accelerometer, 512 hertz. On the left is one of my former students who I'll talk about soon, Paige Madden. She is also a 3-time Olympic medalist. And that's the head coach of the Olympic team from Paris, my friend Todd DeSorbo. So before Kate was a good breaststroker in 2020, she was probably 6th or 7th on the team. We wanted to analyze every aspect of the breaststroke swim, and we found some shocking things about her performance in the part of swimming that isn't swimming. You don't want to lose a race if you are not executing the part of swimming where you're actually not swimming, right? That's like giving away time. So in breaststroke, there's a part of swimming that's called the pullout. It all occurs underwater before the athletes come up for air to start swimming. And if you were paying close attention to the TV commentator when I showed you that video clip, the commentator even says, Douglas is well known for her starts and how efficient she is in streamline. She wasn't before, and this is how we made her efficient. So here's a raw data that we captured from an accelerometer. For anonymity that I'm about to break in a moment, when we share this in public, there was a swimmer called Orange, there's a swimmer called Blue. And this is the underwater pullout. This is where you push off the wall going in that direction. It looks like nothing is happening, and you want to be streamlined. And notice that these two graphs look very different. So the x-axis is time, the y-axis is acceleration. 0 means neither accelerating nor decelerating. And yeah, Kate Douglas is the blue swimmer, and the orange swimmer is actually the current world record holder in 100-meter breaststroke, Olympic gold medalist Lily King. So I think the only part I want to focus on are labeled in this graph. The push-off is very chaotic. The streamline is the part of the swim where you're just trying to go through the water like a torpedo. Then you exit the streamline by executing a dolphin kick to come up to surface. Orange is Lily King. You can see she has basically no deceleration. She's perfect. That's wonderful. You can see that Kate has a much more powerful dolphin kick than Lily's. And that's one of the reasons why we know and expected that she could be a world caliber level breaststroker, because breaststroke is so driven by the legs as opposed to the other 3 strokes. What you notice here about Kate, though, is in the streamline, the part of the swim where the swimmer's literally doing nothing, she's decelerating the entire time. And not only is she decelerating much more than Lily King, she stays in her streamline much longer, exacerbating that deficit. Okay, so we fixed that. Now, you might ask, what is there to fix? Well, as a scientist, you experiment, okay? And so let's analyze just the streamline. This is the part of the swimming that isn't the swim, but we have paid this amount of attention to detail in all aspects of the swim. So let's just talk about the part of the swim where you're not even swimming. So this is October 2020. This is Kate Douglas, and I gave you a little dash line to assist you. That dash line isn't perfect. You can see that she, despite the fact that she thinks she's holding a good streamlined position, is not. All right, where is she now? June 2024, I gave you a little red line to assist you. And the eyes tell you that June 2024, going into last year's Olympic trials, she has a better streamlined position. Yes. What does that little change translate to in the part of the swim that isn't the swim? There's one of these streamlines off the start and off of every wall. It's 0.12 seconds. She holds her streamline that long that we could cut that much time. Now, when you go back and watch the race and you realize she's already ahead because she did something underwater, it's because she's the one that slowed down the least. And she gets this free time off of every wall, off of every wall. She's now the world's best underwater swimmer. Okay, and you'd love to have that time. Okay, is this interesting? Okay, now we think about every other phase. It's exciting when you have time in a part of the swim that has nothing to do with swimming. Good, let's continue. The other story I want to tell you about is about Paige, who's also one of my former students. You might recognize the athlete on the left, Katie Ledecky, generally regarded as one of the best distance swimmers the United States has ever produced. Paige is here on the right, and that's what joy looks like. She gave me permission to share this. Yeah, you might not want this to be the image that that represents your performance in the Olympics, except the Olympics is such a high pressure event. It's the place where you want to swim your best. And you know how hard it is to swim your very best at one particular meet, the best you've ever swum before in your life, but on the world stage so that everyone can see. When you actually pull it off, that's what it looks like. All right, so I want to talk about that. This is Paige. As you can see, she won a bronze medal. She was really broken up about it, out of joy. And I'll tell you, all of us who work the numbers, and we don't have to do the swimming. We knew that if she swam her race, she would be in this position. And actually, that's one of the fun things about the role I play with the elite athletes. They come to listen to me because people have this tendency to believe in numbers. Dr. Ono has the numbers, just don't break his formula. Swim his formula and a good thing will happen. And I like that. Yeah, so let me tell you about the story of this race. Yeah. Oh, and this is what it looks like after the evening celebrating. This is not my son. This is one of my former research assistants at Virginia. He now is in the MIT Sports Lab. He works in figure skating now. So you'll see some of the results of his work in the World Championships or the Olympics in Torino. His name is Jerry. But this is Paige's her parents. Great. Let's watch this race. Can we watch a couple minutes of this race? Because I want you to pay attention. Tell me what you see, and then I'll tell you how we got there. Okay, so the 800-meter race is what she won the bronze medal in. We won't watch it all. We're going to watch the first minute or two, and then we'll watch the last 2 minutes. It's a distance race.
I thought Mike Filippo put
Let me go back. So Katie Ledecky, you saw the names.
Put it best when we talked to him earlier. It was Titmus in the 400. It was Ledecky in the 1500, and now they marry right into this distance. It merges right into the 800, and the strategy for both of them are critical.
As we foreshadow that strategy, Rowdy, to maybe the last 200 meters of this race, you feel it is absolutely imperative that Ledecky has a little bit of a lead with 200 meters left because Titmus has incredible closing speed.
Well, let's back it up for just a second.
This is Paige here.
Right.
He's basically last.
She has to take it out here. She can jump on this first 200, but have it a building feeling, and then she's got to press that pace in that middle 400 dance. That 300 to 600 mark, she's got to lose Titmus because you're right. If Titmus is there at the 600, I think she can take down Ledecky.
She showed that speed.
Okay, so that's the first 116 meters of an 800-meter race. Paige flips at the first 50, almost in last place. The commentators don't even name her, haven't even mentioned her name yet in the coverage. She doesn't exist. She just happens to be an American in the race. All the talk is about Katie Ledecky, Ariane Titmus, and if you're a fan of swimming, these are names that you know, and it's this particular race, which was the last race in Paris for the So I work with a company in Australia. It's called EO Sports Labs, and we make these force paddles that athletes can swim with. And there's a lot of mathematics in there. So if this were a science talk, I'd talk about how we orient the sensors properly to know right, left, up, down, forwards, backwards. Forwards, back, up, down is quite easy. Just measure the direction of gravity. But right, left, a little bit harder. And then how to orient that with respect to the human body. That really is semi-sophisticated mathematics. What do these force paddles do? They record at 512 hertz, basically vectors, 512 times a second. It's recording a vector that comes with two pieces of information: a magnitude, which is measuring the amount of force you're generating with that hand, and a direction in three-dimensional space. And I think most of you are familiar with linear algebra. If not, let me just say it this way. If you know a little bit of linear algebra and you set up the system right, you can determine, so to speak, the efficiency of your stroke. Meaning, every one of those vectors, you take the inner product with the direction that you want to swim, and you want to maximize that inner product, we call that efficiency. We translate that into numbers that are a little bit more friendly, about like percentages, but mathematically, that's what we do with these sensors. So here is Paige. We work with her. And where was she going into the Olympics? In October of 2023, 7 months out of US Olympic trials, her best time in 800 meters was 8 minutes and 32 seconds. That's not even fast enough to get an invitation to swim in the US Olympic trials. Not even fast enough to be invited to be in the meet where we select the team. It's like the 70th ranked. She was like ranked 70 in this event in the United States. That's really not a good position to be in if you want to, A, make the Olympic team, and B, hope for a medal. Yeah, so we studied her with these devices, and I had over the years discovered that she had a difficult time finishing very long races. So I started experimenting with these devices. I had her race men, but I had men swim with fins. Swimming with fins is much easier than swimming without. And I gave the men who would swim in adjacent lanes explicit rules: when to accelerate, when to decelerate. And I gave Paige instructions: when to follow, when not to follow, when to slide over to draft, when not to slide over to draft. So I really wanted to help show that the mathematics and this kind of thinking could be useful in devising strategy. So what did we discover? Well, we discovered something I'm about to show you, and I think the results speak for themselves. She ended up swimming 8 minutes and 13 seconds in the Olympic final, which is still, I think, one of the 6 or 7 fastest times in history. She dropped 19 seconds from October 2023 to July of 2024, going from not being top 70 in the United States of America to one of the best ever in history. That is, the Olympic pool is 50 meters in length. That's over 1 second per length we cut. And that should sound impossible. Now I'll tell you how we did it. Great. So by the way, our device won the Good Design Award. I don't know if you follow these sorts of things. So small advertisement. If you're a swimmer, I encourage you to buy it. There's good science in it. And so what do we discover? So in fine-tuning, Paige, what the mathematics does, and this is just a screenshot of how the mathematics is translated into cartoon graphs, shows quite a bit. So what our devices capture is a real digital twin of athletic performance. So this graphic here is an example of one of our experiments. So you can see in this first column, you see the side view of a swimmer's stroke. The gray is the recovery, the red is the catch, and the blue is actually the stroke itself, side view. This middle column, these two pictures, is the overhead view of the freestyle stroke. Gray is recovery, red is catch, and blue is the stroke. And in terms of the funny data, the inner products translated into percentages are here in these right two panes. So in the first lap, I guess that should say lap 2, my typo. The inner product with the direction of the swim, so to speak, her efficiency is about 59%, which, by the way, don't think math test 90 and above is what you aim for. Nobody gets there. Swimming, people were never meant to swim. Humans weren't meant to swim. So like 60% for that inner product with the direction of the swim, in terms of the force your hands generate, is very good. That's Olympic caliber. What happens here by this lap, this is where I asked Paige to react to a male swimmer who inserted just a little bit of pace. She thinks she's going faster for a short period of time, but you can see quickly here, the overhead view, the digital twin, indicates that her catch, her actual stroke, is crossing over the center line of her body. In other words, her stroke is breaking. What does that correspond to in loss of propulsion? Huge. That 59.1% when she is just concentrating on her stroke, when she reacts to another athlete, breaks, and that drops to 42%, and 15% of her effort is steering her to the left. And you can tell that that's not good. Now, for a short period of time, you can adjust the pace of the stroke to keep up. But in a long distance race, that accumulates over time. And if you watch these races, there's a line of swimmers going out, a line of swimmers coming back. And then as the laps go by, people fall off, and then Katie Ledecky wins. That's generally how it goes. And our test indicated that Paige really should never be falling off Katie Ledecky, so we wanted to know why. And what we discovered is that in the heat of competition, when she reacts to an athlete on her right, accelerating, her stroke breaks. And we wanted desperately to fix it. We were never able to fix it because it's a mental thing, right? We just were never able to fix it. And that's not a criticism of Paige Madden. That's very common, probably among the top 20 800-meter swimmers in the world that are always losing to Katie Ledecky and Ariane Titmus. Maybe half of them have something like this. So what was our recommendation? Strategically, when she tries to match acceleration on pace with somebody on the right side, she starts crossing over like this. Her propulsion drops, and the force is just misdirected. So what was our strategy? Our strategy was simple. Forget anyone else is in the pool. Swim your race. Swim in your lane. Forget anyone else is in the pool. You've been swimming for years. If you're going to go out in the Olympic Games, you're going to swim your race, following your strategy as if no one else is in the pool, because the moment you start racing, we think you're going to break your stroke and it's going to fall apart. Did she do it? Yeah. Not only did she do it, she swam the first 400 in 406.5, and she swam the second 400 in 406.5, down to the 100. It's actually 5-0. She exactly even split it. Olympic level athlete knows how to, they're metronomic, and that was awesome. So she got a bronze medal. I have 2 comments about this. I wanted to talk about how even this thinking can help the strategy. I think the results speak for itself, but there's a little bit more to that. So in conversations with the coaches, it got to the point where we said to Paige, and this is Todd's idea. He goes, before the Olympic finals, there's a short period of time where you can warm up in the Olympic pool as the crowd shows up. Most of the Olympians are in a back pool, out of sight with their coaches. And Paige swam in her lane that she was going to swim in with the Olympic bells and whistles in this stadium. The energy is incredible, and trained herself. I'm going to swim in this lane by myself right now, tune everyone else. There literally will be nobody else in the pool with me, and I'm going to repeat it when the gun goes off. And that's what happened, and it was awesome. And that's why I'm really proud of that race, because it's how the mathematics actually changed a strategy, and I think it speaks for itself. By the way, if you're not a close follower of Olympic swimming, I will tell you that most of the events in the Olympics and the World Championships proceeds through a series of qualifying rounds: preliminaries, semifinals, and then finals. But that's not true for the longer events. The 800s, it's preliminaries and finals. If the 800 meter race in Paris had been prelims, semis, and finals, this would have been her semifinal swim. Think about where she would have been if she had exerted herself on the first 50 just to stay in the line rather than being last at the line. I don't know that she would not have won the gold medal. And that would have been really something to talk about. She doesn't like talking about it because winning an individual medal at the Olympics is an awesome thing, and you can often overrate what it means to be gold versus bronze or fourth, right? Being an Olympian is a big thing. And so this is the race that I really wanted to tell you about. So in any event, we also work with swimmers of all ages. We now work with Masters World Champions. They will be in Singapore shortly after the conclusion of the Pro World Championships. Here are some names that you might know if you follow World Champion swimming for this age group. And these swimmers swim as fast as many collegiate athletes, and they're in their 60s. And what I like about it is they are the easiest swimmers to help. Do you know why? If you're a 60-year-old elite swimmer, you probably swam in college in the early 1980s when people didn't understand as much as they do now about swimming. So it's very easy for us to teach them some of the developments that they didn't have access to because they ended up having their own careers. And so, yeah, I predict that Jelena and Fred will probably win 5, 6 medals at the World Championships, and I will be disappointed. Almost money back guarantee kind of stuff that they'll set world records, and we're so confident of it on our website. There's something called Project World Record, and I think their social media presence is all about that. And I think it's awesome because they're in their 60s, and it shows that love of sport is not something that's restricted to youth. Awesome. So my time is up, but I was going to analyze other things that we do for swimming, but I think you get the idea. Any movement that might be perfectible, we study. We break down each swim by the meter. And by the way, our school team, the University of Virginia, broke the American team 200-meter freestyle relay. 4 athletes, each swimming 50. And we set the American record without a single swimmer who was in the top 20 individually. That should sound impossible. But how does this work? If you swim in a pool, there are walls here and here, there are flags here and here, and what we perfected is we wanted our athletes to have the shortest time from flags, hit the wall, flip turn, hit the wall. We had the fastest turns in the country, and that was enough to set a record. The part of swimming that isn't swimming, the efficiency of the execution. Right? So we think about how quickly do you raise your knees coming into a turn. We think about what is your angle of rotation coming off a wall to maximize. So we think about all these little things. And you know, 1/10 of a second here or 1/10 of a second there are usually easy to find for athletes who've not been trained at that level. If you're in a club and your coach has 60 athletes, you're all doing the same thing. None of them have been optimized. The moment you can optimize, maybe you'll get 3% faster. And I think that's where the science comes into play. So I hope this was interesting, right? Swimming fast is not about effort. It's far more cerebral than many of the other sports, which is why I like it. So yeah, so I could have shown you a lot more, but yeah. So there's a story behind every one of these graphs. Yeah, is anyone here a swimmer? Oh, you're swimming, triathlon, okay. So when you take a stroke in backstroke or freestyle, at what point of the stroke do we want your hands to be moving the fastest? The beginning or the end? The beginning or the end? The end. If it's moving very quickly at the beginning, you're probably slipping. You probably haven't captured as much water as you want. So we study very carefully the rate of speed of your hands, like centimeter by centimeter through the stroke. When you integrate that, you get something like this picture. So you can see this is an Olympian. His name is Ryan Murphy. And you can see that his hands at the beginning of the stroke are going at 1.16 meters per second, but at the end is at 3.11 meters per second. And this was Yelena. She was 2.11 meters per second at entry and 0.89 at exit. And so we had to completely break her stroke. She's been swimming this way for 40 years. So we had to completely break it so that she was quite intentional about catching maximal water and getting a real, what they call feel for the water. And you know what? That is a second per lap. You make that change. Great. Anyway, I think you'll get the idea. I hope this is interesting. So yeah, no, I said even more than that, 1 to 2 seconds. Yeah. And all she has to do is, I think, find about half a second to set the world record in backstroke. She might break like the 45-year-old, the world record for 45-year-olds in her 60s. That's what I'm hoping happens in a few weeks in Singapore. Great. And so, yeah, if you're interested in more, the press likes it. I've resisted writing articles in sports science journals because I don't want to deal with the refereeing process. I already have to do that as a professional mathematician. So I would rather work directly with the athletes and the coaches, and it's actually it is fun. I teach a class at the University of Virginia to swimmers. It's kind of funny. This is Kate Douglas that I've talked about quite at length here. This other girl here, she swept the World Championships in backstroke last year. She won all 3 events. She's a favorite, one of the favorites to win the 200-meter later this week. And they just happen to also be great math students, so I like that very much. Great. Any questions? Yeah, okay. Yes.
Thank you for a really nice talk.
Yeah. This is fun.
Pass mics around for the questions, I guess. There's people online trying to listen.
So my question is more from the scientist side is,
Yeah.
so you are fairly trained in very abstract things like string theory and the number theory, representation theory, etc. How was it to switching into something which is so real life, much more, let's say, physical application? So how was that journey?
Super fun, right? If I go to a party and say, I study number theory, nobody wants to talk to you, right? Look, you all came to hear about swimming, right? I like that. I mean, I certainly like talking and working with my graduate students. It's something like that. But the transition was actually quite easy.
Okay, no, I mean, my question was more like how was it difficult to understand like the techniques or everything what's real scientists use, or like sports scientists
so
use?
I'm just using scientific principles I think that every scientist would use. Yeah. The hard part in the early going was getting buy-in from elite coaches. But now I have people calling all the time now. But at the outset, were you an Olympic swimmer? No. And then people don't listen to you until Andrew, right, wins a gold medal. Yeah. But I was very honest when I said, I'm not a good swimmer. I understand all the things that you're not supposed to do, because that's what I'm good at. I'm good at being bad at swimming. That's a good place to be. In fact, some of the best teachers are the ones that give the best explanations, because the ideas that they teach didn't come to them naturally. Do you know what I mean? Yeah. Like Shohei Ohtani, could he be the best baseball coach? Maybe he's the best baseball player, but could he be who knows? Some of the best baseball coaches were actually horrible baseball players. They understood their flaws and dreamt for more, and they decided to go into coaching because that was the way to achieve. Yeah.
Thanks for great talk. So I noticed in the breaststroke that they lift their arms out and sort of move them forward above the water.
Yeah.
So does the reduction of drag by doing this, is it not offset by the arched?
Yeah, so it actually depends on the athlete. So even considering the tempo, so you'll see if you go back and see Kate swim, you'll see she's doing something a little bit different from everybody else, including the tempo. So the answer is we measure that. And even how you bring your arms up is highly individualized. So the answer is it depends on the athlete, but generally you're right. And we call it the praying mantis. Yeah. Yes. There's no one answer. So you'll discover you can ask me lots of questions and I will rarely say, yes, that's exactly right, because it is so dependent. It's the precision training part.
Thank you. Yes, in answer to your question, it is very interesting. Actually, I went to your talk the other day and I misheard. I thought this talk was going to be about how to gamble in swimming, like how to know. And at the end of the talk, I realized, okay, yeah. I mean, I was wrong, but I was right.
We don't want to gamble.
So my question is, hypothetically, how will you coach a horse?
I wouldn't. I'm not a coach, by the way. If,
No.
if I sound like a coach, I'm not a coach. I give information to the coach, and the coach has to deal with the personality. Some of that's pretty horrible.
Yeah. I mean, where would you put your sensors, for example?
I would first have to study how horses run first, but you can put sensors anywhere. Yeah. You can put them on skis. People now put them on ski boots. Not to as great effect as people would like because the sport is so fast.
Cool. Hi guys, can you hear me? Yeah, great talk, and thanks for coming to OIST. I guess early on, this talk was so incredible, information dense. But earlier on, you made a comment about how you're in the you want to use the science rather than ending up in like a journal, but actually practice, and get outcomes right now. And do you kind of remember talking about that? When you were saying that, I was actually thinking about like entrepreneurship and product market fit. Like we have a lot of scientific research here. How instead of ending up in research, which is in scientific publications is important, but how can we turn that into entrepreneurship?
That is an excellent question. In fact, we wrote a white paper about this exact issue earlier this year at the University of Virginia when the NSF and NIH announced their cut to overhead. Federal funding for research in the United States is not being threatened, it's vanishing. And so it makes you rethink the entire scientific enterprise. For my entire career, I have been in a position where I could count on reliably taxpayer money supporting my grants for my research, and I cannot count on that anymore. That's not reality. So you have to think very quickly. Fortunately, there are some foundations that come to assist you, but there's not enough of them. For every grant that the Simons Foundation would like to support, they can perhaps only support 30% of them because science is expensive. And so what we discovered is there are models now, and we're actually participating, and I'll give a couple examples in a moment, where the scientific expertise at the university is partnering with industry with specific benchmarks in mind that are completely different from the traditional university research model. For my entire career, it was about get your grants, write these papers, hope to get in these journals, and you will succeed, and maybe you'll get some honors along the way. That has now been completely turned on its head. Your expertise, whether it's in chemistry or physics or whatever, might be very valuable to an immediate application in the real world that a company needs, whether it's in drug discovery, and they're scrambling for funds, whether it's in climate change, where maybe there's a company that's trying to think about reducing waste in the railway system because the pollutants fly off. All those are like real problems that science can address. And those benchmarks won't be, the benchmarks there aren't scientific publications. It's really immediately, did your work matter? So if you work in fields where there's the prospect of partnering with a municipality or an industry where there's that need, well, we already understand that that could be a source of funding, and it's actually rather satisfying. It's interesting that you say that. If I write a paper, maybe it gets accepted in a top journal. I can give you a name and it might not mean anything to you, but it might transform my life. But that's just in my little world of mathematics. There's journals called Annals, Invenciones. Ask people, if you're a mathematician, get those papers, it changed your life. But if you're not a mathematician, those are just words to you. But what if the mathematics that we do somehow improves the internet or makes the internet or cybersecurity more robust? That's something you can all understand. And often the mathematical tools are already there. So to answer your question, and I'm glad you brought it up that way, because I didn't think of it this way. Maybe one of the reasons why I like the swimming is I can in real time see the benefit of the scientific process in performance, and I don't have to justify it through some article that says, here's a table that, right? And maybe that's part of what underscores this paradigm shift. That's
amazing.
Thank you.
Thank you.
Yeah. Oh, I was going to give you examples. So in mathematics, we are very lucky. Many of us working in mathematics are in demand from the AI labs, Google DeepMind, OpenAI, and regrettably Grok, who is funded by Elon Musk. But me and my community and many people in my sphere are thinking about how to improve the mathematical reasoning of chatbots, studying the reasoning traces. And yeah, that progress is on the one hand exciting, on another hand, absolutely frightening. But I think we all should be engaging in that, because I think it is realistic for all of the sciences, from basic sciences through the applied sciences, to benefit from AI. And the applied sciences has already happened, right? Large language, right? A human being can't read an MRI scan as good as a computer, right? You can't beat a computer at chess, but you can beat it with creativity, the skills that these models do not yet display. And that's, for me, the question when people talk about AGI, is the time coming where these AI entities exhibit that? I think the answer will be no, but the bar and what defines that might become frighteningly high. When we say an idea is creative because you borrow one idea from one field and introduce it to another, will AI be able to do that? I've seen that. So in the course of our work, we want to focus on, those skills.
Two things. First, are you suggesting we never prove anything again? Because that would be
No,
fantastic.
of course not. No. Right. So, but I mean, suppose you
I was just joking.
yeah. So, no, but absolutely. Yeah.
It reminded
no, I
me of
understand that, but yeah, okay.
It reminded me of your talk the other day. That guy who didn't want to prove anything.
Oh, yeah.
Yeah, that was cool.
If all we had to do was make conjectures all day, right? That's like the world of wishful thinking. Yeah. Science doesn't proceed that way. I wish something to be true, so I declare that it is true, and then voila. It just happens to be how science is done by policymakers in the United States right now. That'll be short-lived, right? There will be some.
Sorry. Have you been approached to analyze a more complex? This is super complex, obviously, but something more, not so linear kind of thing. That's how it feels in my head. Like, for example, I was actually working in a university where someone was studying climbers, and that gets really complicated. Like I had questions, like they actually approached me because I climb, and they, oh yeah, you're a mathematician, can you help me? And I was completely lost, because first, it's not my field, obviously, but I was thinking, like, how do you even, every single thing is different. At least in climbing, you have one goal, and every single climb you can optimize to be, or allegedly, right? But something as complex as climbing, like not every single climb is the same.
Right,
So
and not every climber is the same.
Yeah.
But unlike chess, every human being playing chess, maybe one has a stronger right hand than the other, but it doesn't matter. That'd be much more interesting, right? If you had like 100-pound, I mean, yeah. So I don't know.
So I imagine if you were to do some sport that it's a bit more complex, how things change.
Yeah. I haven't done it, so I can't answer. People are interested in using some of these tools in team sports, but I have to tell you right away, swimming is not a team sport. It's all about perfecting an individual's performance, where all you have to do is study that individual and only how that individual interacts with water and walls. That's all I have to understand, and that's hard enough. So yeah, good question. That's not for me. Yeah.
Thanks for the talk. This is probably not an easy question, but you showed us how mathematics, and more generally science, can result in a better performance of an athlete at the professional level. So you demonstrated your commitment to science and what it spits out, particularly mathematics, to improve that. What is your take on mathematics when it shows, well, this particular person is incapable of competing at that professional level? You study that person, and then you come to the conclusion that you should communicate morally and kind of scientifically that, well, give up, you're not built for this particular purpose. And I think that is another aspect of mathematics, isn't it? Like you prove right or wrong.
So I will make a comment about that. I don't think that the goal should be only winning Olympic medals and world championship medals. I mean, I talked about these master swimmers who swim for the love of sport. But let me go a little bit further than that. I want to point out that there has never been a finalist in the World Championships of swimming from a third world country in the modern era. This never happened. It has never happened. And you can imagine why it has never happened. First of all, you need to have a swimming pool. There aren't many of them in third world countries. Secondly, economics matters. If you don't have a background, a financial background that allows you to spend 20 to 30 hours a week training to perfect your swimming because you can't afford it, you cannot be a great swimmer. So as awesome as some of these performances are, I don't think we've gotten close to what is humanly possible in any one of these strokes and events, because the sheer number of people that have had an opportunity to train as much as our athletes do in sport is remarkably small. And
realistically speaking, that will never happen. We know that, like no matter how we think, how we fantasize the future life, like equal condition will never exist.
So maybe, but I'm more of an optimist than that. So World Aquatics, that runs the sport of swimming in the world, they have assembled a committee that has taken on what I just described to you as its charge. Their dream is to have an athlete from a third world country at the Olympic Games in Los Angeles make a final and hopefully medal, and they are investing in those countries. It's imperfect, but maybe they will reach 1,000, 2,000 swimmers in Africa and certain countries in Southeast Asia. Maybe it will happen. I know, but this is the point that I really want to get across. Yeah. The other question is about, I didn't answer your question. What can I offer you? Yeah. Yeah, so we have a number of drills that we test, from box jump to power and amplitude of her dolphin kick. She was outperforming the men on our college team. And remember, by that time in breaststroke, I'd already worked with Andrew Wilson, who was an Olympic medalist. And I'm seeing her stats line up very close to him. So much better than everyone else. So we just had to assemble the swim, teach her the mechanics, and get the timing right. And you see it now in. Often, there's a lot of little things. If you swim and at 15, your high school coach says you're a backstroker, how do you know that was actually right? How do you know that was really the event that was made for you? You might grow and outgrow it, discover you're better at another event. That's what some of our tests aim to discover. If you don't swim for 1 week, you swim a whole lot slower. So subtle changes can result in major time drops. And so we don't take at face value that someone coming to the university who historically has been swimming one event really can't be much better in another event if we teach them how to swim it. I honestly believe this. I think I could take everybody in this room and you could have a performance in the top 3% of your age group. That's how much I believe is lacking in most training. I'll say that again. I don't believe that there's anyone in this room that after a year of hard training, weightlifting, some analysis, but really training, couldn't be top 3% in your age group. That's how little attention is paid to the science of swimming. Try to walk through water, it's hard. Try to swim through water, it's hard. You don't just muscle your way through. Yeah. It's the person that slows down the least if they are fit. Oh, maybe.
Excellent. If
Sign up for
anyone
swim
has
clubs.
more questions, feel free to come and talk to Ken after the talk. For now, I think we should thank Ken again for a lovely talk. Thank you all for joining and for many interesting questions.